Okay, so we are going to have a second presentation by Samantha Creech, the physics, and the faculty advisor is Dr. Britt Green, and her topic is the galactic winds and probing the gas of the early universe. And again, each presentation has 20 minutes, and that includes 50 minutes of the presentations and 5 minutes for question and answer. At 30 minutes, I'm going to show you this 2-minute sign so you know you need to wrap it up. At the 15 minutes, then I will stand up and try to let you know that your presentation time is up. At the conclusion of 20 minutes, then I have to kick you off, and then that's what I'm going to do. Okay, so for the students coming late, then please silence your smartphone and have a good courtesy. Thank you.
The early universe is a place of chaos. Galaxies are constantly smashing into one another and tearing each other apart. Violent bursts of star formation result in equally violent explosions as massive stars go supernova, and these collective explosions drive winds out to great distances, or so we think. The early universe is a place of chaos, but we don't know much about it yet. It's very far away, very dim, and as a result, very difficult to observe. That being said, supercomputers have opened doors for astronomers. Simulations give us a way to plug in all the physics that we know, or think we know, plus play on time, and then make predictions on what we expect to see when we look out into the universe. But these theoretical simulations can only take us so far. Observational astronomy comes up behind the theorists and finds clever ways to test the predictions that were put forth by simulations. And my research project fits snugly into this gap between theory and observation. My name is Samantha Creech, my mentor is Dr. Britt Lundgren, and I've been doing my research on gas in the early universe. So, returning to that early universe, as gas condenses and begins to form fragments of early galaxies, many of these rotating clouds will flatten out and form disks with beautiful spiral arms. And as these young galaxies grow, their increasing gravity draws in more and more of the surrounding material. The surrounding material is called the Intergalactic Medium, quite literally meaning the stuff between galaxies. And as it comes in onto the galaxy, it too flattens out, spiraling in along the plane of the galactic disk. This means that when you look out to great distances from any given galaxy, you should still expect to find traces of faint, diffuse gas. Next, zooming into the plane of the disk itself, this infalling material is causing rapid bursts of star formation. And when you have a lot of stars being born, you'll inevitably have a lot of massive stars that live short lives and die spectacular deaths. The resulting explosion is called a supernova, and it creates a bubble of rapidly expanding gas. So when you have a lot of supernovae going off at the same time, the expanding bubbles of gas reinforce one another and create large-scale winds that are funneled out of the galaxy along the rotation axis and perpendicular to the plane of the disk. This means that you should see these cone-shaped structures that are perpendicular to the disk of the galaxy. More often than not, this outflowing wind doesn't reach the escape velocity of the host galaxy. It then rains back down and is drawn in again, along with this inflowing intergalactic medium, and the cycle begins anew. So, taking these two phenomena together, the inflowing gas along the plane of the disk and the outflowing gas along the rotation axis, you get a pretty good idea of where you should and shouldn't expect to find gas surrounding a spiral galaxy. And this model has been well supported by simulations, but few attempts have yet been made to actually observe it in the early universe. So before I go on, I just want to briefly cover what I mean when I say look back into the early universe. As many of you probably already know, light travels at a finite speed, 3 × 10⁸ meters per second, and this is ridiculously fast. And we observe it as instantaneous in our everyday lives. But the universe is ridiculously big. So when you look at galaxies that are farther and farther away, you're seeing photons that have taken longer amounts of time to get to us, and you're effectively looking into the past. The particular galaxies for this study are anywhere between 6 and 9 billion light years away. So we're looking at the universe as it was when it was practically a baby. And when we look at this baby universe, there are a couple of key predicted differences between what we expect to find and what we do observe when we look at the modern universe. For one, in today's day and age, star formation is slowing down. There are fewer stars being born, and as a result, there are fewer supernovae going off. So the winds that today's spiral galaxies produce are pretty wimpy, and they don't make it out very far before they fall back onto the plane of their host galaxy. Inversely, the early universe is absolutely bustling. Star birth and death alike occur at an incredible rate, and the result is a much stronger wind. So when you look at the gas that's being produced by galaxies in the early universe, you should expect to see that it's reaching much faster distances than we observe coming from today's modern spirals. Okay, so now we have a good idea of what we expect to find, and that's great, but how the heck are we going to see it? This gas that we're looking for is incredibly diffuse, far more diffuse than even the best vacuum that we can make on Earth. And to make matters worse, it is kiloparsecs away from any star that could light it up, and it's cold. Hot gas glows, but cold gas is pretty much invisible. What we need is something external to these clouds of gas to help us probe at it and show us that it's there in the first place. What we need is a flashlight. Okay, what do I mean by flashlight? We need a bright light source that is far more distant than the clouds of gas that we're looking for. And even though these clouds are very diffuse and almost invisible, they will still cast a slight shadow of sorts. The light that we get back from our flashlight is a wee bit dimmer than we would expect it to be. These shadows are called absorption lines, or absorption features. And they're called absorption lines because when you spread the light from our flashlight into a rainbow, they appear like distinct dark bands at very specific colors. And there's a really interesting property about the universe. By analyzing the colors of these absorption lines, you can extract a lot of important information about the gas that produced them. Of particular importance here, you can figure out how far away the gas is, and you can figure out what it's made of. Using the distance, we can then match these clouds of gas with equally distant galaxies. So find the galaxies that are probably responsible for that gases being there. Using the composition, we make sure that we are only looking at gas that has already been processed by stars. That way we don't risk accidentally poking into random clouds of intergalactic medium that actually have nothing to do with the galaxy. But in order to poke at these clouds at all, we need something that is very, very bright. And what kind of object can actually probe at these clouds of cold, dark gas that we're looking for? We use something called a quasar. Quasars are some of the brightest things in the entire universe. Oftentimes, they completely outshine their own galaxy. And for this reason, they make a great flashlight. So, using the light of the quasar, we can find absorption lines from clouds of gas. Using the absorption lines, we can extract the distance of that gas. Using the distance, we can match them up with galaxies. And here's where my project officially comes in. I spent my summer analyzing the galaxies in 8 of these fields that were taken with the Hubble Space Telescope. And when we turn to this data, what exactly is it that we're expecting to find? Let's turn fast back to what we already know. We have a quasar. We know about clouds of gas that rest between that quasar and ourselves. We know how far away this gas is, and we know about galaxies that are at the same distance as us to this gas, so galaxies that might be responsible for its being there. The next step is to figure out if these galaxies match the description that our model has predicted. That is, disky spiral galaxies with either the planes of their disks or their rotation axes pointed towards the quasar, so towards the gas that we've detected. And in order to find this, we need to know 4 things. We need to know the coordinates of the galaxy and the coordinates of the quasar within the image. We need to know the position angle of the galaxies, and then we also need to know the galaxy's morphology. That is, whether it's a disky spiral, an elliptical blob, or something irregular in between. We already had data telling us the coordinates of the galaxies and the quasar in the image, but in order to get the morphology and the position angle data, we used a program called Galactic. The way that this works, you feed it a picture of a galaxy along with a text file that contains some parameters. These parameters include things like Circic index, axis ratio, radius, and position angle. Galactic basically uses these parameters as a starting block, and then tries to build a toy model off of the galaxy that you fed to it. Now, if the parameters that you type in are so wonky and messed up that Galactic doesn't know what to do with them, it'll spit a nuclear bomb out at you. But this only happens on a very bad day. Most of the time, Galactic already has its own idea of what that galaxy should look like. It'll then calculate its own parameters and give you an idealized model of the galaxy. And this model is where we get our data from, the morphology and the position angles. Next up, Galactic tests the reliability of its own model. It basically uses that image to try to sort of Photoshop the galaxy out of the original picture. Ideally, you should then be left with nothing but the noise of the background sky. No traces of your galaxy left behind. Now, this is one of the most beautiful and ideal examples that I came across, and I'm very proud of it, but I galvatted on the order of 180 galaxies. Most of them didn't look this good. Such as this one. Now, oftentimes, Galvat would produce a reliable model with reliable data, but it would still leave some residual behind. And this could happen for a variety of reasons. The galaxy could just be very bright, or it could have some extra structures to it, like an active galactic nucleus, a star-forming region, spiral arms. Galvat does have the ability to take these away, but it won't do that unless you really force it to. And that takes a lot of time and a lot of nuclear bombs, so for the sake of finding a position angle, it's really not necessary. Now, quick side note. To keep myself from going crazy when I was in my windowless lab, I made a game out of giving these galaxies different names. So this is the Toenail Galaxy, officiated by me. And here's the reason why I was going crazy in my windowless lab. These galaxies, remember, are 6 to 9 billion light years away. So a lot of them were very small, very dim, or very smudgy, and Galvat wouldn't be able to build a reliable model off of them. You can always tell by looking at that residual image. For instance, if your entire galaxy is still left behind, or worse, your galaxy's been replaced by a tiny black hole, you know something's not right. You know that that model doesn't well describe the galaxy, and you can't trust the data that we get from it. Now, this is bad, but some days Galvat just doesn't know what it's trying to do. That last picture is supposed to look like the noise of the background sky, and it does not. So, disasters of this proportion were usually caused by an error on my part. They were relatively easy to fix. Contrary to what you might expect, it's these mediocrely terrible models, where the galaxy itself is just intrinsically too small or dim or weird for Galvat to know what to do with, that often ended up having to be scrapped from the data. So after those months of galvatting, this is a histogram of the results. The black line up top counts up the total number of galaxies with any given position angle with respect to the quasar. The blue just shows galaxies that were not matched to any of the gas that we found, while the red and the black are galaxies that were matched to this gas, with the black being those most likely to actually be responsible for it. And the way that this histogram is structured, if you see a galaxy matched to absorption that is at 90 degrees with respect to the quasar, we're probably probing at the center of those cone-shaped outflows. And if you see a galaxy at 0 degrees, we're probably looking at that inflowing intergalactic medium. So I'd like to point out some interesting results. First off, the peak of this histogram occurs at just about 60 degrees, not 90. That means that instead of catching the center of these cone-shaped outflows, we're looking at the lip of them. Now, what does that entail? Well, theory has already predicted that these outflows should be more concentrated about their circular edges. So if you have a quasar shining through the edge, it's passing through a thicker cloud of gas and creating a stronger signal than a galaxy that's shining through the center. And then here's the same result, but plotted in a slightly different way. Here, the vertical axis, the horizontal axis, represents the distance of the galaxy with respect to the quasar. The radial axis shows that galaxy's position angle with respect to the quasar. So each point on here represents an individual galaxy that was matched to absorption, with the circles being those most likely to actually be responsible for the gas that we found. That means that the other points, those plus signs, could be responsible for the gas, but more likely than not it was the circles. So if you go along the radial axis and find the point that says 60 degrees, then trace a line back to the origin, you'll come across all the points that contributed to that peak of the histogram from the previous slide. Now, you can see by looking at this that we're seeing evidence of winds reaching as far as 140 kiloparsecs away from their host galaxy. And that is huge. That's the equivalent of almost 460,000 light years, 4 times the diameter of the Milky Way galaxy. And as a comparison, in the modern universe, we usually only see winds reaching as far as about 40 kiloparsecs before it falls back onto the galaxy. So just as we predicted, we're seeing evidence of winds reaching much faster distances than we see in today's day and age. And there's a second interesting result hidden in the depth of this plot. The color of each point represents the star formation rate of the galaxy. The pink correlates to a very low star formation rate, while the blue are galaxies with very high star formation rates. And since the outflowing winds, which would correspond to galaxies at 60 degrees and above, are produced by collective supernova explosions, you might expect that these galaxies should have a very high star formation rate. But when you look at this plot, that's not necessarily the case. A lot of these star formation rates are very low, and some of them are effectively zero. Does that make any sense at all? Well, if you think about it, this wind that we're seeing has had to travel for millions of years to get from its galaxy to our line of sight. So, star formation is not a constant thing. It's very sporadic, especially in the early chaotic universe. And what's more, when a galaxy is driving out large amounts of wind, it can effectively starve itself out, because the same gas that it's blowing away is exactly the gas that it needs in order to make new stars. So by the time this wind reaches the point in front of the quasar where we can detect it, the galaxy could very well have starved itself out already. Now, all of these results are exciting. They match the description of what we expect so well that my mentor asked me if I'd somehow biased the data. And if the results are in fact real and not just caused by random chance, they show us that our understanding of this piece of the puzzle is on the right track. The one pitfall is sample size. Through the data cuts that we made and the 8 fields that we ended up using, we only ended up with about 80 reliable galaxy models. And 80 data points isn't much. In fact, it's kind of amazing that we are seeing such a strong trend with such small data. In the future, we hope to get more time on this Hubble Space Telescope. This will allow us to get more precise data, expand our sample size, and gain a sharper insight into that chaos of the early universe. Thank you, and are there any questions?
We have 3 minutes for questions, please. 3 minutes. Does our Milky Way emit any galactic light or waves?
Sorry, one more time?
Does our Milky Way emit those galactic waves too? Galactic, whatever beams?
Yeah, I believe it has winds blowing out of it.
From our Milky Way. Will they contaminate what you have found here?
No, the way that we find these absorption lines and trace it to gas is by looking at specifically where it appears in the light of the quasar. So if we were to catch gas from our own galaxy, it would appear in a different spot than gas from the early universe.
I was just going to ask you, what was your favorite part about the process, and if you had to do it again, what would you change?
My favorite part was probably when we finished all of the gal fitting and just sitting at research meetings and staring at these plots and making science out of them. And what I would change, there were a couple of times where I went through and gal fitted half of the galaxies in a field and then realized that I had done something wrong. Oh. So I'd probably tell myself not to do that.
So one last question is, did you write that GalFit program? It's a program, right?
It is a program. I did not write it. It's an open source. Yes?
What's your favorite galaxy that you named yourself?
I'm a fan of the Hunchback Whale Galaxy. Or the Spiraling Asteroid of Doom Galaxy. That's a good one too. Yes?
Why do you think that some of the galaxies didn't match GalFit? Why couldn't GalFit handle them?
It's just usually because they're so small that whether they're a disk or an elliptical galaxy, it's hard to tell because they don't take up many pixels. The signal to noise is not as great as we would like it to be, because this is a very dim part of the universe.
Okay, thank you.
So how many pixels do you need in order to get a reliable calculation?
I don't know the specific number of pixels. It's just as long as the galaxy is big enough to really be able to tell what the structure is. That's something that I still need to test, is going through and seeing how big a galaxy needs to be before the results are reliable.
Okay, thanks for coming.